Thank you. OK, so I want to define some problems. And before that, I need to give you some definitions. So I am working on the symmetric group on some finite number of elements. And I want to define a metric. And the metric is going to be just for two permutations, sigma and tau. The distance between sigma and tau is computed as follows. I take all the values from 1 to n where they differ. I count how many of them there are. And I normalize. So I get a number between 0 and 1. OK, so this is just the Hamming distance between them. I would also like to have a distance between tuples of permutations. So if I have k permutations in sim n, and let's call them sigma 1 up to sigma k, and also tau 1 up to tau k, again, all of them in the symmetric group of size n, then I say that the distance between those k tuples is just the sum of the respective distances. So for me, those distances are the amount of work I need to do to turn this tuple into this tuple. If at each stage I can make, let's say, a small change to the permutations. So this is the amount of work I need to do to turn this tuple to this tuple. And just another slide about notation. I would also like to define, to use the well-known concept of distance between a point and a set. So I just want you to know what I mean. If I have a tuple of k permutations and a subset of this space of k permutations, then distance between a tuple and a set is just the minimum realizable distance. Those are finite sets, so I can say minimum. The minimum over the distance between this given sigma to any tau in A. Okay. So now I can use this to tell you of a result. Let's, for every n, let's consider the space commuting n. This is just the space of pairs of permutations which commute. Okay, so inside the space of pairs of permutations, it's a very small set, but we define it nonetheless. And let's first look at this thing that I called an exercise. If I have two permutations, then there are two ways in which I can say that they almost commute. One way, on the right-hand side, is to say that the distance of this pair of permutations to the space of all of commuting permutations is small. If I say that this value on the right is small, then they are close to the space of commuting permutations. Another way to say that they almost commute is to say that the sigma tau and tau sigma are very close to each other. So these are different notions. It's not the same thing, but it's not hard to see that if I have two permutations, sigma tau, which are close to this subspace, then sigma tau and tau sigma must be almost the same. Yes, because if sigma and tau are close to commuting permutations, then I just take two commuting permutations. And for the commuting ones, this distance is 0. And then I make just a few changes, so it cannot change this distance by much. So permutations which are close to the space of commuting permutations are almost commuting. But the interesting thing is that there is also a theorem in the other direction. So this is a result of Arjantseva and Paunescu that says that if I have permutations sigma and tau such that the distance between sigma tau and tau sigma is very small, then they're actually close to the space of commuting permutations. Okay? So let's just see exactly what's written here. I'm not expecting a linear expression like I have here, but for some f, which approaches 0 as x approaches 0, the distance of a pair of permutations to the space of commuting permutations is at most this f times the distance between sigma tau and tau sigma. And the important thing about this result is that this function f is the same. You can use the same function for all n, no matter how large the permutations are. This is the major point of this result. Otherwise, if you can think about it, if f was allowed to depend on n, then this would be a triviality. Okay.
Depend on how it depends on n.
Well, yes, if you allow it to depend on n however you want, then this is a triviality. Yes, that's right. Okay, so the title of this paper is Almost Commuting Permutations Are Nearly Commuting Permutations. And it's completely non-constructive. It has no information whatsoever about this f because of several compactness arguments in the paper itself and in the papers that it uses. Okay. I want to spend one slide on property testing to explain one motivation to study this. So what we had in the previous slide is summarized here. And now I want to say that if I have a pair of permutations, then checking if they are close to a commuting pair is something that I can test probabilistically by only looking at a constant number of places. Let's do this. So take some delta for which this function f is smaller than 0.1 in this interval 0 delta, and take some k such that 1 minus delta to the k is very small. Now what I say is that if I have two permutations and they are far from the space of commuting permutations, 0.1 far, interesting. So if I have a pair of permutations that are far from this space, then if I independently choose k numbers from 1 to n, and for each of these k numbers, xi to xk, I plug in xi both to sigma tau and to tau sigma, and just check if I get the same value. If they really commuted, I must have gotten the same value. But if they are far from commuting, the chance that I will miss the fact that they are not actually commuting is very low. Okay, and this is a three-line proof given this result of Arzhanchev-Aponesco. So but the proof is just if the pair is far from the space of commuting permutations, then by the deep result, this distance to this space of commuting permutations is smaller than some function of the distance between sigma tau and tau sigma. And then, just by the way I picked delta, that this distance between sigma tau and tau sigma must be large, which means that there are many places where those permutations differ. So if I just plug one of the xi's, I have a probability of detecting this which is bounded away from 1. So if I just repeat it k times, I can get very low probability of missing the fact that they commute, so very high probability of detecting it. Okay. Right. So now I will explain a generalization of this problem. Yeah, let's spend a few slides about that. So we've considered so far the equation xy equals yx. I like words in the free group, so let's move everything to one side. It's the equation commutator equals 1, equivalent, of course. And more generally, I can take any free group with base x1 up to xd. And for any word in this free group, I can ask the same questions about the equation w equals 1, where w is the word. Right? So the question is it true that any almost solution to w equals 1 is close to an actual solution? Is it true that any permutations which are close to the space of solutions to this, no, sorry, any permutations which almost satisfy this are actually close to the space of solutions to w equals 1? And I don't have to look just at a single equation at a time. I can also look at the system of simultaneous equations. Okay. So let's define this formally. I have this free group, and for any word in the free group and a tuple of d permutations, where d is the number of generators of this free group, I write W of this tuple for what you get, the permutation you get by substituting xi, the sigma I instead of xi, inside this word W. So yes, I just replace each formal letter xi by the permutation sigma I, and I get a composition of permutations. So this is what I denote like this. And then if I have a finite set of words, then I have a space of solutions, which are just the tuples, which are solutions. When you substitute them into the words of this set E, you get an identity. Just an example to see that you're with me, the set of solutions to this singleton, which only contains one word, the commutator of size n, is just the space of pairs of commuting permutations of size n. This is what it means. Okay, but here I'm allowed to take a singleton, and I can also take larger sets, and I'm considering simultaneous equations. So I'm looking for something that solves all of the equations in the set simultaneously. Right, so, and now I can make the general definition that the system of equations W equals 1 for each of these finite sets of words W is stable with respect to the symmetric groups with the normalized Hamming distance if for every n, which is the size of the permutations, and a tuple of permutations of size n, d of them, which is the number of variables in the system of equations, I have the same type of inequality. This is a measure of how of the distance from satisfying those equations, right? So for yes, there is the parenthesis here on the wrong side. But what I do here is that I take each of the equations, and each of them I substitute sigma into W, and I check how far it is from the identity. Let me just write what should be written there. It's a sum of the distance between W when you substitute sigma to the identity, where I run over all the equations. Okay, so in the case of a single equation, this is just a sum over one element. And I ask for the same thing. If the equations seem to almost hold, then I want the distance to the space of solutions to be small. If there is such function f, which goes to 0 as x goes to 0, then I say that this system of equations is stable. And again, it says that I can test whether or not a given tuple is close to this space of solutions. Here's another way to say this. So I can for some non-negative delta, I can define a delta solution as just a tuple for which this number is small. Yes, again, the parenthesis should be here. So this tuple, again, is the sum of distances of the substitution of sigma to the identity. And for epsilon, if I have two tuples, sigma and tau, I say that they're epsilon close if their distance is at most epsilon. And then I can give the same definition in different words. I can say that this system of equations is stable with respect to the symmetric group with the normalized Hamming distance if for every epsilon there is delta, such that for every size of permutations n, every delta solution in the symmetric group is epsilon close to an actual solution in the symmetric group. This is just the same claim. Okay. So every delta solution is close to a solution, and the point is that this epsilon delta dependence is before I introduced n, so it does not depend on n. Okay. So far, I took a system of equations, and I wanted to say yes or no. Is it stable or not stable? So I just split the world of all system of equations into two parts. It turns out that some system of equations are almost equivalent. So I want to treat them as the same thing. So for this, I want to define what it means for a group to be stable. Take in the previous setting, I had a free group and a basis, and I created equations. Now just take this whole setting twice. Take one free group with the basis F1 with basis S1 and F2 with basis S2. And for each of them, take a finite subset of words. And then its effect, an elementary fact, but I will not prove it now, that if the group presented by those generators S1 with the relations E1, and the group presented with S2 generated by S2 and relations E2 are isomorphic as abstract groups, then either both these systems are stable or both are not. So it makes sense to study them together. So somehow these two systems of equations are equivalent. Well, using this fact, I can also define what it means for a finitely presented group to be stable. It's just take a finitely presented group gamma, take one presentation, finite presentation of gamma, and then say that gamma is stable if the system of equations you get from the relations is a stable system. And this is well defined because of this fact. It doesn't matter which presentation of the group I took. So this is not how to prove, but it enables us to use group theory to study those equations. Okay. Yes. This f function, it will only differ by a multiplicative constant.
Depends on the presentation size.
Depends on the presentation, yes. But only multiplicative constant.
So where is n
Yes.
in this? I mean, this fact is, I find it confusing.
Well, this is, with respect to, this should be
No,
from,
upstairs, the fact. So you have two groups.
stability is not with respect to a single n. Stability means that for all n it holds.
But it's a single group, so it's an infinite group.
It's an infinite group. Well, usually, if it's a
It's a finite group, it's an empty statement.
well, it's an easy statement.
Well, because the constant swallows everything. There's no sequence of groups, so it's an empty statement.
No, I need to explain again. So I'm always looking at solutions in the symmetric group. Always. What?
Oh, even sorry.
The only thing I said now is that sometimes I have two systems of equations and they are actually equivalent. This equivalence is defining the same group. But I'm always studying stability in the symmetric group. I'm just saying that group theory allows me to say that two systems of equations are essentially the same when you study stability.
Lets you express one equation in terms of the other.
Yes, that's it. Right? So it's just like I'm always looking at stability in the symmetric group, but let's say that I could study the equations x, y, y inverse x equals 1, or I could study the two equations x, sorry, this should be x, y. This is just commutator equals 1, or I could add that also, I take this commutator equals 1, and also the inverse commutator equals 1, but this is implied by this one, so it doesn't make sense to study this separately. I'm just saying that equivalent presentations should be studied together. So this is trivial, but it really opens the door to many techniques. I'm going to spend 2 slides on a more general concept and then go back to the symmetric group. So far, I only considered almost solutions and solutions in the symmetric group. But I can do this same for any sequence of groups with metrics. I can define what a solution is and what an almost solution is. So no, just they can be completely not related groups.
Distance should be normalized.
Well, but you don't have to for the definition. So just, let's ahead of time take this example of take the unitary groups with the L2 norms, the Frobenius norm, I mean. These are infinite groups, but you can just do the same. If I study the same problem of the commutator equation with respect to this unitary group, then it will be the problem of whether almost commuting matrices are close to commuting matrices with respect to this norm. So although I will focus on the symmetric group, I want to spend one slide on this particular example of solutions in the unitary group with the L2 norm to explain some relation to this particular conference we have. Okay. So this is a theorem of the Shifre-Glebsky, Lubotsky, and Andreas Tong, which is built from the following 4 parts. This is an inapproximability result. These are about some groups which cannot be approximated locally in the unitary group. I'll talk about approximability later a little more, but I hope you can get a general sense what it means. So using Garland methods and some method of Deligne, they construct groups which are first not residually finite. It means that the intersection of finite index subgroups is not trivial. And two, there are 2 Kashdan groups, which is a variation of property T. It just means that the second cohomology in all Hilbert spaces vanishes instead of the first one, which would be property T. And they prove that those 2 Kashdan groups are stable with respect to the unitary group and the L2 norm. Then a simple observation is that if I have a group which is stable in this sense and not residually finite, it cannot be approximated by matrices with this norm. So it's a theorem about the existence of groups which cannot be approximated in this norm. So Garland method, so it's related to this conference. Okay, but now back to the symmetric group. From now on, when I say stable, I mean stable with respect to the symmetric group with the normalized Hamming metric. Okay. Some previous results. A theorem of Glebsky and Rivera says that finite groups are stable. Let's say again what it means. If I have a system of equations, and this system of equations, when you think about it as a group, it defines a finite group as a presentation, then this system of equations is stable in the symmetric group. Every almost solution to the system of equations is close to a proper solution. So this is a result about finite groups. Arjantseva and Panesco said the same thing about abelian groups. So the result that I told you before, that almost commuting permutations are close to commuting permutations, is actually the result that z squared is stable. And in general, abelian groups are stable. And here's a negative result. If you have a stable Sophie group, then it must be residually finite. So you can ignore the word Sophie for the moment and just say that most stable groups that you will encounter must be residually finite. The Sophie, I'll explain it later. But let's just say for now that no group is known to be non-Sophic. Okay. Let's take an example of this negative result. This group Baumstark-Solitar 2-3, which is defined by a single relation, ba squared equals a cubed b. It's a Sophic group. It's known to be Sophic. It's also known not to be residually finite. So these equations, ba squared equals a cubed b, is not a stable equation. You have almost solutions to these equations, which are no way near solutions. So from group theory, I am able to say something about stability of an equation.
Can we write down examples of this?
Yes. You unravel the proof that it is sophic and it is residually finite, and from the constructions in those proofs, you create permutations.
In principle, doable, but is it doable?
No, it's all explicit. You just have to follow many steps.
Have you done it?
Well,
If I closed
No.
you in the room and said you will only leave when you write me a solution.
yes, for sure. I mean, following this is not a big deal, and following the sophicity, I know all the steps. I did not draw the. I did not.
No, it would be interesting to
Yes.
see.
And also to see how, as dependence on n, what's going on here.
So maybe I'll do it on a Monday.
It is not difficult to write. I mean, how not difficult? It's construction. Write matrices which almost satisfy this.
Yeah,
Matrices
it's
of-
interesting to understand, what's going on, how this happens.
Mm-hmm.
It's, the stable case is easy to imagine. You have commuting.
Mhm.
You change it a little bit, and it's almost here. No. To come up with stupid examples for almost commuting is very simple. I think for every equation.
Well,
Take
actually,
something that satisfies the equation, you change it a tiny bit, and then you can come back. These are uninteresting examples. These would be, I think, much more revealing.
I see. But okay, so I can say something then. So for this particular group, the hard part is to prove that it's sophic, but not that it's residually finite. And what it means is that if you take those permutations that give me this negative result, I can look at the graph whose vertices are the numbers 1 to n, and it's the graph of the action by those two permutations. From each point, I have two outgoing edges, one by applying one permutation and the other by applying the second permutation. It's just that the local profile of this graph cannot appear in any actual solution. There is some local obstruction there, but it's a local obstruction, but it's not something that you see. I mean, you need to go a little far to see this local obstruction, but it's there. So
Sounds very interesting. We'd really love to see it.
sure. Okay. Here is an if and only if for the stability of amenable groups. Let gamma be an amenable group, then it is stable if and only if every IRS, don't be afraid, of gamma is cos-sophic.
No taxes?
Yes. So this is a joint work with Alex Lubotsky and Andreas Tom, and I will not assume that you know all the terms that I've written here, so I need to explain what an amenable group is, what an IRS of a group is, and what it means for the IRS to be cos-sophic. First, amenable groups. I'll just work with finitely generated groups. So let gamma be such a group, and a sequence of finite subsets of gamma is a Fellner sequence if first I wanted to exhaust the group, so the union needs to be all of the group, and second, it needs to have, as a sequence, zero isoperimetric constant. So what's written here? This is S. S is the finite generating set of gamma. So S times gamma is everything that you can get by starting, S times Fn is everything you can get by starting from the finite set Fn and working with one generator. But I remove the set Fn, so it's all the neighbors of Fn which are not in Fn, and then I normalize by the size. So this is just the size of the boundary divided by the size of the set, and I want this to approach 0. So this is like a highly non-expanding sequence, and then a group.
It's Chigger constant 0.
Yeah. And then a group is amenable if it by one definition, Fellner's definition, is that if it just has some sequence. So if you were looking at something like z squared, then you can take squares, and there are finite sets with this property, of course. So more generally, you can take solvable groups. You can take Fellner sequences which are analogous to the squares in solvable groups, and some very different groups like Rigorchuk's group. So this is a whole field, amenability. The second thing, I want to explain what IRS is. So it's invariant random subgroups. If I do it just for finitely generated groups. So take some finitely generated group and consider the space sub gamma. These are it's just the space of all subgroups of gamma. A random subgroup is a probability measure on sub gamma. And a random subgroup is invariant, and an invariant random subgroup is a random subgroup, which again is a distribution on subgroups, such that for any subspace of the set of subgroups and an element of the group, the measure of this, the probability to be in this subset is the same as the probability to be in the subset after conjugation. Okay, so this is an invariant, a random subgroup which is not affected by conjugation. And those spaces have topologies, and they are compact. And convergence in IRS gamma is the weak star convergence, or some people call it the weak convergence. And now I can say what it means for an IRS, for an invariant random subgroup of gamma to be cos-sophic. So it is cos-sophic if it's the limit of invariant random subgroups which are only supported on the finite index ones. Okay. So this is, well, I'll say something in the next slide.
I'm sorry,
Yes.
couldn't parse.
Sure.
So IRS gamma.
IRS gamma is the space of invariant random subgroups gamma. It's
in
a
space of distributions?
It's a space of distributions, spatial ones, only the ones that are invariant under conjugation.
Sure. And you're saying that it's cos-sophic if this space is obtained
No,
by
no,
the limit of
no, sorry. Yes.
An element there is
N IRA, right. What?
Okay. Every element
An
in the
element
space
of IRS is cos-sophic.
becomes cos-sophic if it's the limit of this space.
Yes, yes. Thanks. Each element can be, each invariant random subgroup, each distribution can either be cos-sophic or not. It's not a property of the group, of the space. Okay. So now that we had a course, let's see the theorem again. Gamma is stable, for an amenable group is stable, if and only if every invariant random subgroup is cos-sophic. Here's another way to say it. Gamma is stable if and only if the space of invariant random subgroups, which are supported on the finite index subgroups, is dense in IRS gamma. So stability for amenable groups is a density property of some subspace of the invariant random subgroups in the whole space.
So that's why you made that mistake. That
Yes, yes. Mm-hmm. So I have the space of all invariant random subgroups of gamma. I have the subspace of such invariant random subgroups which are supported only on finite index subgroups. And if this smaller space is dense in the larger space, then it is equivalent. This is an equivalent condition to stability for amenable groups. And now we can apply it. So the previous result, the previous positive results that I showed you was that finite groups and abelian groups are stable. But now I have something much more general. Polycyclic groups are stable. So polycyclic groups are groups which have a subnormal series. It's just a series of subgroups. Each one is containing the previous ones. You start from the trivial one. You get to the entire group. And all the quotients in between are cyclic groups. So this is a big generalization of abelian groups. And they are all stable. Another result, the bounce-like solitar 1n groups, which are not polycyclic, they are defined by these single equations, BA equals A to the n B, for any fixed n, they are stable too. And also I have some negative results using the same criterion, which answers some open question. I won't get into this. Let's summarize in 3 bullets what we did. I'm summarizing from the end. So using some results in group theory, you can study the invariant random subgroups of those groups. Then, using the criterion that we proved, my work with Lubotsky and Tom, you can apply your knowledge of the invariant random subgroups of these groups to determine stability or instability. And then, by the basic observations of this theory, you know the stability or instability of the defining equations of those groups. So using group theory, some very classical things about profiler topology of groups, eventually I can deduce stability or instability of some equations. Okay, let's survey some other results. Another theorem with Alex is that if you have an...
Maybe just to give the psychological effect of it, it's kind of psychologically influenced by gamma theory. Gamma theory tells you that if the equation is solvable, if and only if the group associated with it is solvable in the group theoretical sense. Here, the equations are stable if and only if the group is stable, but to determine whether the group is stable is a much more difficult issue. But once you do it, you really deduce something about equation, which elementarily it's completely inaccessible somehow to get to the equation and to decide if they are stable or not. It's really using called group theory to say something about something very concrete equations.
Okay, so far I talked about amenable groups. Let's go to the other extreme and talk about groups which have Kashdan's property T. So let gamma be a group which is infinite, sophic, again this word that I didn't explain, and has property T, then it is not stable. Okay, this looks like a very strong result, but let me just say that the proof suggests that one may take some weaker notions of stability, and this entire thing will still be may be interesting for property T. So although this looks like we know everything, we can change the definition a bit and then we know nothing. And it will be very interesting. I can tell about it in some other time. So maybe it's time to say what a sophic group is. Yes, well, the main theorem did not require knowing it, so I didn't explain, but the group is sophic if its Cayley graph can be approximated by finite graphs. If you want something more accurate, it means that for any radius r and epsilon, there is a finite age-labeled directed graph x. So a finite graph with direction and the same labeling as in the Cayley graph, the same labels on edges, such that almost all balls in these finite graphs are isomorphic, almost all balls of radius r are isomorphic as balls to the one in the Cayley graph. So this is one compact way to say what a sophic group is. It's a group where you can have finite groups which locally almost, finite graphs, sorry, graphs, not groups, which locally almost everywhere look like the Cayley graph. And many groups are known to be sophic, but no group is known to be non-sophic. Nevertheless, people do believe that non-sophic groups exist. Let me end with the quantitative aspect. Yeah. Let's go back to the abelian case. So I'm looking at this system of equations, xi, xj equals xj, xi, for some d variables, x1 up to xd. So these are the defining relations of the free abelian group z to the d. And then I just repeat the definition of stability here. This system of equations is stable because there is such f. This is the definition, such that if I have an almost solution to to these equations a tuple of permutations which almost commute pairwise, then I know that they are close to the space of real commuting permutations, but the Arjantsev-Apaonesco result doesn't tell me anything about how small f is. And I want f to be small. I want to say that the distance to the space of solutions is very small. In terms of the stability, it means that I don't have to check many places in the permutations to determine probabilistically whether or not they are close to the solutions. So this is a work in progress with Jonathan Moshev. So it's not completely written up yet. We're working at it. But it says the following: for this particular set of equations defined by the commutators, there are some constants C and D, which depend on the number of variables, but on nothing else, such that the function, the constant m times x to 1 over c works. So this is not such a horrible function. If you try to extract the function f by turning the original proof, most compactness arguments can be replaced by a pigeonhole principle. And if you try to do it, you immediately see that you are going to get some Taylor of exponential. So this is much better. Eventually, we will have an explicit value of c, but currently I cannot tell you exactly what it is. And I think it's 2, but I don't think we'll prove it.
I think we have 4.
Let's not give a number.
Can you say why do you need like this, that it's abelian or amenable, like the opposite of expanding for stability? How is that useful?
No, they have a theorem even that says that
Yes.
when you go to property P, there is no stability.
Yeah, so I want, so can you shed some light on this?
Mm-hmm. Yes. There used to be an eraser. No, but this is not for this board. Yes, the organizers are just זה יעבוד. So let's say that I have, let's work with 2 permutations, sigma 1 and sigma 2. And then yes, I'm not sure what I'm going to draw, but let's draw a grid. So if I take a grid and then let's take some square in the grid. So think about this grid. Take those are permutations in the symmetric group of on n elements. And this grid is part of a graph on the points 1 to n. So I have n is very large. I have the points 1 to n. I have this graph on the points 1 to n defined by those 2 permutations, where x is an edge going to sigma 1 of x and to sigma 2 of x. And here is a small portion of this graph which happens to look like a grid. So what I can do, I can take just a square in this grid, and because it has very small isoperimetric constant, it is? It is. So I mean, these are the vertices. And then I can take this this square and there just because I can change the permutation that from here, instead of going to the right, go here. and I can close it. Because the boundary is so small, it's not expensive to close everything. So I can take a portion which looks like a grid and extract some finite orbit of the action of sigma 1 and sigma 2, which is perfect. There will be no mistakes on these vertices.
You blame the failure of the equation on the peripheral side. And when
Yes.
it's small, it's a relatively small.
Yes, because I want to work just a little bit. But it turns out that what I'm drawing here is very, very simplistic. And to actually prove a quantitative result, one needs to go to the theory of lattices in Z to the D and some results about geometry of numbers. Because people have studied efficient basis for lattices in abelian groups. And we are dealing with abelian groups, and we want efficiency. And it turns out that the same thing that people studied for things like the LLL algorithm and so are also good for the efficiency that we are seeking. But this is like way over what I can describe now. Thanks.